So now we've talked about the action potential and the action of the voltage-gated sodium channels and the voltage-gated potassium channels, and how that creates the action potential and the inactivation of the sodium channels. Now let's talk a little bit about the unidirectionality of the action potential as it moves down the axon. As the wave of depolarization moves, it only moves in one direction due to the inactivation of the sodium channels. The depolarization is going to open sodium channels, but only those that haven't been inactivated and are within reach of the depolarization. And so that's going to create a unidirectionality. The proof of this is if you artificially injected current into the middle of the axon, say, you would see the wave of depolarization move in both directions because there wouldn't be this trailing edge of inactivated sodium channels behind it. And so the unidirectionality of the action potential comes just from the inactivation of the sodium channels, and so by the time they become closed and active again, the wave of depolarization has moved far enough away that it can't be affected. And so if you haven't done so already, you're going to want to watch the action potentials video so that you can understand where this unidirectionality comes from. In addition to that, we can talk a little bit about where the speed of neuronal signaling comes from. And basically, if we were talking about wires, resistance comes from the diameter of the neuron. And so when we were talking about those squid giant axons, they were big and fat, and so because they were so big around, there was very little resistance. But our neuron cells are much thinner in diameter, and so there's going to be a lot of resistance. We couldn't just rely on the wave of depolarization per se to do neuronal signaling, because it wouldn't be fast enough. Plus, there's a chance that we could get some amount of shorting out from one neuron to the next. So if one neuron fired, it could affect a neuron right next to it. And we wouldn't want that. And so in order to have coordinated motor behavior, we've created something called the myelin sheath. The myelin sheath is created by oligodendrocytes in the CNS, or the Schwann cells of the PNS. And the cells, the Schwann cells, are just cells that, as they grow, they wrap around the axon, and that creates an insulation around the cell, much like the plastic insulation around small wires in electronics. And in between these Schwann cells are unmyelinated regions called nodes of Ranvier. And these nodes of Ranvier are the only places where the sodium channels are able to interact with the extracellular sodium milieu. And so what happens in the motor neuron is that the depolarization jumps from one node of Ranvier to the next node of Ranvier, because those are the only available sodium channels to open that have extracellular high sodium content. And so really, we've got the action potential moving equally and undiminished, jumping from one node of Ranvier to the next node of Ranvier. We call this saltatory current. How it jumps equally and undiminished from one node of Ranvier to the next, maintaining the strength of signal from the beginning all the way down to the axon terminus. So what happens at the other end? Once the wave of depolarization reaches the axon terminus, what happens? Well, this all dates back to Lowy and his discovery of neurotransmitters, chemical signals. And so what Lowy did was he stimulated the vagus nerve, a neuron that a nerve that was known to slow down the heart. And so he did this in frogs, and so he stimulated the vagus nerve of one frog and collected the liquid from around that frog, that heart, and then he squirted that liquid onto a second heart, and it slowed down, proving that there was some sort of chemical. We now he called that chemical vagus stuff after the vagus nerve. We now know that that chemical is acetylcholine, and that acetylcholine binds to muscarinic acetylcholine receptors in the heart, and they're G protein couple receptors that we're going to talk about later in chapter 16. But the action was that it slowed down the heart because it took the neuron further away from excitation, or further away from that threshold potential. And so now we know that that we're releasing some sort of chemical, and it turns out that that the neuron, the axon terminus, has lots of vesicles that are filled with neurotransmitters, and these neurotransmitters are released by the vesicle binding with the membrane. So these neurotransmitter-filled vesicles bind with the membrane and release their contents into this place, this 40 nanometer across space that we call the synapse. They drift across and bind to ligand-gated ion channels, or chemical-gated ion channels. And so in the case that I'm showing you here, we've got sodium channels that are responsive to NMDA. So these vesicles are full of glutamate, full of glutamate, and this glutamate binds to the NMDA receptors, or the kainate receptors, opens them, and then sodium is allowed to rush in the second cell. And so that's how signals are transferred from one cell to the other. Because what happens is, as the wave of depolarization, the action potential, invades the axon terminus, it causes voltage-gated calcium channels to open. And this calcium acts as a signal to the vesicle. So these vesicles get loaded with neurotransmitter, the chemicals, and then they dock and get primed using V snares and T snares, and we'll talk more about that in the intracellular trafficking chapters 15 and 17. But these V snares and T snares are going to wind up like corkscrews, pulling the vesicle membrane closer to the cell membrane until it fuses. And then anything on the inside of that vesicle will now be on the outside of the cell. The trigger for them to wind up together is a protein called synaptotagmin. And synaptotagmin will only do that in the presence of calcium. So voltage-gated calcium channels open, calcium rushes in, binds to the synaptotagmin, and causes vesicle fusion. And then all of the proteins in the vesicle are then going to be recycled using receptor-mediated endocytosis, or clathrin-mediated endocytosis. And so vesicles can be full of lots of different chemicals. They could be chemicals that are going to bind to sodium channels and cause an excitatory postsynaptic response, or maybe that open potassium channels or chloride channels. In those cases, we would have an inhibitory postsynaptic response. And so we're just going to have the postsynaptic and presynaptic responses summed over the cell body using temporal and spatial summation. And the key is if at the axon hillock it's ever greater than the threshold potential. It's estimated that it takes about 10 or 11 more excitatories than inhibitories in a close approximation to the axon hillock to cause the action potential. But once the action potential starts, then it moves down the axon equally and undiminished. And when it invades the axon terminus, then it causes calcium channels to open, voltage-gated calcium channels to open. Calcium rushes in, causes the synaptotagmin to cause the V snares and T snares to bring the vesicle in contact with the cell membrane, and once fusion occurs, then the chemicals that are loaded in those vesicles go into the synapse, travel across that 40 nanometer space, and bind to receptors on the other side. We've got excitatory postsynaptic potentials being summed. Maybe they will reach threshold, maybe they won't. But if at the axon hillock the threshold potential is ever reached, then we have the action potential, which is the sodium and voltage-gated sodium channels opening, causing the rising phase, voltage-gated potassium channels opening, causing the falling phase. The overshoot is then resolved using the sodium-potassium pump and the leakiness of the potassium channels. So that is a little bit more about the ins and outs of how it works at the synapse, as well as how it moves down the axon. So that's it for chapter 12, and now I guess that's all the information for the first test, and if there's anything you don't understand about anything from the first test, we need to resolve that at the review session. Okay, thanks.